Good morning, ladies and gentlemen. My name is Jordan Padu, along with my colleagues Eric McHaleson and Anthony Gerbic from the Department of Electrical Engineering and Computer Science at the University of Michigan. We would like to present to you our work on dual-band stacked metasurface reflectarrays. In order to design the dual-band stacked metasurfaces, there are three main ideas or contributions. The first is we homogenize the reflectarray. The fine features of the sub-wavelength elements are homogenized and modeled as a single impedance sheet. Next, we formulate an integral equation which models the full mutual coupling between the impedances of the homogenized reflectarray. Since the elements are sub-wavelength and homogenized, the currents are treated as nearly uniform, and thus one pulse basis per homogenized element is necessary. Third, we develop an iterative algorithm to simultaneously design the array layers at both frequencies. We will explain this iterative design cycle later in the presentation. Here we briefly describe the Metasurface concept. The fine features of the sub-wavelength reflectarray elements are homogenized when the probing wavelength becomes long and the medium properties become averaged. The metasurface will exhibit the same scattering parameters as its homogenized sheet model as shown in the upper right of the slide. Rather than modeling the currents on the pattern geometry, we model the currents on the homogenized equivalent. Since the elements are sub-wavelength, the currents are nearly constant and thus only require a single pulse basis to model. A simple boundary condition relates the total electric field on the homogenized elements to the surface currents and sheet impedances. The metasurface design boundary condition is negative n hat cross E total equal to A to sheet times the surface current density J. We use the metasurface design boundary condition to design the sheet impedances of the stacked metasurface. There are four simple steps to follow. 1. We determine the desired total electric field on the metasurface. 2. We express the scattered field in terms of the surface currents. 3. We solve for the currents using the method of moments. 4. We determine the required sheet impedance from the metasurface boundary condition. We will outline these four solution steps in the following slides. In step 1, we determine the desired total electric field. The total electric field can be written as the summation of the incident field plus the scattered field. Since the incident field is known from the specification of the feed, only the scattered field remains to be determined. Since the scattered field phase is stipulated as part of the design, only the scattered field amplitude remains as unknown. To find the scattered field amplitude, we look at the total field power density along the metasurface plane. The total field power density can be written as 1/2 the real part of E incident plus E scattered crossed H incident plus H scattered conjugate. By expanding the product, three terms are generated. The first is associated with the power density of the incident field. The second term is associated with the power density of the scattered field. The third term is associated with the interference between the incident and the scattered fields. To satisfy local power conservation, we have to set the total field power density equal to 0 at all points along the metasurface. We set the scattered field power density equal to the negative of the incident field power density. We can thus find the amplitude of the scattered electric field through this equality. This leaves only the term associated with the interference between the incident and scattered fields. The term associated with the interference between the incident and scattered field alternates between positive and negative values. The figure on the upper right shows the incident field power density in the blue curve, the scattered field power density in the red curve, and the power density associated with the interference between the incident and the scattered field in the green curve. The black curve shows the difference between the incident field power density and the scattered field power density and is equal to 0. The interference term oscillates between positive and negative values, as alluded to before, but when integrated over the metasurface plane, leads to a 0 net power. The presence of the power density associated with the interference terms leads to the necessity for lossy or active elements at the locations where either positive or negative power is required. Alternatively, one can shuttle power from locations along the array of positive power to locations where negative power is needed using surface waves. These designs are therefore called non-local power conservation designs. In this slide, we investigate the effect of the power density associated with the interference term on the sheet impedances. Shown in the upper left is the sheet impedance of a typical single-layer metasurface designed to scatter an incident cylindrical wave into a reflected plane wave. By expanding the vertical axis and investigating the real part of the sheet impedance, we can see that points along the metasurface where there is a net negative power density lead to negative sheet resistances, and points along the metasurface where there is net positive power density lead to positive sheet resistances. These active and lossy sheet impedances are difficult and costly to manufacture and thus should be avoided. In this slide, we show our technique to avoid the real sheet impedances. The iterative design cycle presented later in this presentation allows one to throw out the real part of the sheet impedance during each cycle of the iterative design and ultimately converge upon a purely reactive sheet. During each pass of the iterative design cycle, the sheet impedances are calculated for each layer at each frequency. Each time they are calculated, we throw out the real part and keep only the reactances. The additional degrees of freedom of the multi-layer design allow us to converge upon purely reactive sheets. In step 2, we construct the electric field integral equation for the stacked metasurface antenna. The multi-layer geometry is shown in the upper right of the slide. It consists of 5 layers, 2 metasurface layers, 2 dielectric spacers, and 1 ground plane. For observations made on layer 1, we can write the metasurface boundary condition in the following form. E incident is equal to E total minus the scattered electric field from the surface currents on layer 1 minus the scattered electric field from the volume currents in layer 2 minus the scattered electric field from the surface currents on layer 3 minus the scattered electric field from the volume currents in layer 4 minus the scattered electric field from the surface currents on the ground plane. This integral equation was constructed for observations made on layer 1 only. Similar integral equations are developed for observations made on the remaining layers. In step 3, we expand the unknown current densities appearing in the terms of the electric field integral equation into one-dimensional pulse basis functions for the surface currents or two-dimensional pulse basis functions for the volumetric currents. We employ Galerkin testing in order to transform the integral equation into matrix form and arrive at the matrix equation shown in the bottom of the slide. This matrix equation is the discrete analog to the continuous EFIE derived in the previous slide and can be solved on a computer. Repeating the previous steps of writing the integral equation and transforming it into a matrix equation for the remaining layers produces 5 total matrix equations. All 5 coupled discretized volume surface integral equations can be put into a block matrix form. By solving this block matrix equation, we can solve for the currents on each of the 5 layers. We solve the block matrix equation using a guess and update iterative solution scheme. Since the volume impedances in layer 2 and layer 4 are known from the volume equivalence principle, only the sheet impedances on the metasurface layers of layer 1 and layer 3 remain as unknown. In the block matrix equation, we have highlighted these unknown values in red. Since the stacked metasurface antenna is designed at 2 frequencies, a similar block matrix equation must be constructed for the second frequency. For the discussions of this slide, we will concentrate on the block matrix equation for frequency F1. In step 1 of the 4 design steps for the design of the sheet impedances of the stacked metasurface antenna, we determine the desired total electric field along layer 1. The scattered near and far fields are related to these aperture fields. Since we know the total electric field along this layer, we can express the unknown sheet impedances of layer 1 in terms of it. We can thus eliminate the sheet impedances as unknowns. In the block matrix equation shown above, we have expressed the product of the sheet impedances along layer 1 and the current density on that layer as the blue W1 matrix, which is formed from samples of the total electric field. Thus, only the sheet impedances along layer 3 remain as unknowns. To solve the block matrix equation, we make a guess for the sheet impedances of layer 3, which linearizes the system, solve the matrix equation, and then update within a loop. The update made within a loop of the design cycle is described on the next slide. As alluded to before, in this iterative design cycle, we throw out the real part of the sheet impedances for layers 1 and 3 during each iteration, which allows us to converge upon a purely reactive sheet solution. The guess and update iterative solution scheme details are provided in this slide. As alluded to in the previous slide, in step 1 we make a guess for the sheet impedance of layer 3. The made guess linearizes the system and allows the matrix equation to be solved. By solving the matrix equation, the unknown induced currents on each layer are determined for the case of the sheet impedance along layer 3 being that of the initial guess. With knowledge about the total field on layer 1 and the induced currents on layer 1, the sheet impedance of layer 1 can be determined. By the usual frequency scaling laws for impedances, the sheet impedance of layer 1 at the second frequency can be determined. Because we now have the sheet impedance and the total field along layer 1 at the second frequency, we can solve for the induced currents along layer 1 at frequency 2. Because there are now only 4 unknown surface currents, we can reduce the system of 5 matrix equations into a system of 4 by removing the matrix equation describing layer 3, which has the unknown sheet impedances along that layer. We can then solve this new system of 4 matrix equations for the remaining unknown surface currents. We then return to the matrix equation for layer 3 that we removed and solve for the sheet impedances of layer 3. Now we know the induced currents on all of the layers and the impedances of all the layers at the second frequency. We then use the usual frequency scaling laws again to obtain the sheet impedances for layer 3 at the first frequency and update our original guess. We continue this process until convergence is achieved. As a reminder, in each cycle of the iterative design algorithm, when the sheet impedances are calculated, we throw out the real part and keep only the reactances in order to converge upon a purely reactive solution. Upon convergence, the sheet impedances for layer 1 and 3 are determined using the formulation shown in this slide. This completes step 4 of the 4 design steps for design of the sheet impedances of the stacked metasurface antenna. As an example, we use the design algorithm to design a 3-layer metasurface reflectarray operating at the frequencies f1 equals to 5.1 GHz and f2 equals to 2.4 GHz. The dimensions of the taconic RF41 substrates and the metasurface layers are shown in the lower half of the slide. The converged upon sheet reactances for both frequencies are shown in the figure to the left. These sheet impedances at the 2 frequencies are related by the usual frequency scaling laws. The sheet reactances are purely reactive and show slow variation. We imported these sheet impedances into COMSOL multiphysics and calculated the scattered far field patterns at both design frequencies and compared it to the result of the method of moments algorithm. The agreement is excellent, validating our design algorithm. In order to realize the sheet impedances in pattern geometry, a library of printed reactive elements must be compiled. There are 5 elements in the library: a gap capacitor, an interdigitated capacitor, a parallel shunt resonator capable of shorting at 2 different frequencies simultaneously, a straight transmission line inductor, and a meander line inductor. The range of reactances achieved by each of the elements versus the range of the geometrical parameter for each of the elements is shown in the table provided on the slide. The extraction of the sheet impedance for the various geometries must be performed at the 2 frequencies and for the different cases of layer 1 and layer 3. In layer 1, the element is placed at the interface between an infinite half space of air and an infinite half space of dielectric. In layer 3, the element is placed in an infinite space of dielectric. The frequency dependence of the various elements in the various cases are provided in the figures at the top of the slide. We note a slight deviation from the usual frequency scaling laws for impedances used during the design. Thus, after the elements were designed and characterized, the actual frequency scaling was used in the design and the stacked metasurface antenna was redesigned. We use these geometries to realize the sheet impedances in a patterned cladding stacked metasurface antenna and obtain the scattered fields through COMSOL multiphysics simulations. The patterned metallic cladding for layers 1 and 3 are shown in this slide. The uppermost figure is the patterned metallic cladding for layer 1. The middle figure is the patterned metallic cladding for layer 3. The lower figure shows both layer 1 and layer 3 when viewed from below the ground plane. Although the uppermost layer looks like a constant impedance, the interplay between all of the layers form the desired response, and the slight perturbations in the capacitive reactance of layer 1 are necessary to achieve the overall response. In this slide, the pattern geometries are placed within the parallel plate waveguide in order to emulate infinite geometry in the vertical direction. The stacked metasurface antenna is excited by an infinite line source. The result of the COMSOL finite element full wave simulation is shown in the lower right of the slide. The scattered field phase for both the lower band and the upper band are shown. The scattered field phase resulting from the simulation of the patterned metallic cladding stacked metasurface is compared to that of the scattered field phase of the homogenized impedance sheets version at both frequencies. The agreement is excellent. The scattered far fields of the patterned metallic cladding stacked metasurface antenna at both frequencies is shown compared to those from the method of moments algorithm. The patterns show excellent agreement, validating the element geometry, impedance extraction, and metallic cladding patterning process. In conclusion, we presented a design algorithm for dual-band stacked metasurfaces. Our developed design technique models the intra-layer and inter-layer mutual coupling on a homogenized model accurately. An iterative guess and update technique was developed to allow the designs at both frequencies simultaneously. The proposed approach does not have limitations on the frequency separation. And a dual-band stacked metasurface reflectarray antenna design was presented. Full-wave simulations show excellent agreement with our design algorithm. Finally, I would like to thank you for your attention and acknowledge our sponsors. This work was supported in part by the Office of Naval Research and the Army Research Office. Thank you for paying attention to my presentation.